Hi KCET 2026 aspirants, so welcome back to the Sankalp series where we have taken a pledge that we will work every day harder and harder to get into the top 1000 rank in KCET 2026 examination. So bachcha log, till now what we have studied in Haloalkanes and Haloarenes chapter. So in part 1, let us quickly recall it, okay? So in part 1, we have a brief introduction. We said hello, hi to the Haloalkanes and Haloarenes. We knew how to call them, how to nomenclature them, how to give their names, right? How to classify them. In part 2, where were we? In part 2, we were in labs and we were doing different reactions, different reagents we were taking, and we were preparing these dynamic powerful molecules. But today is going to be where we are exploring the real chemistry behind these molecules or real power of these molecules. Okay, why? Because we are going to discuss about the reactions of haloalkanes. Okay, now trust me, this is going to be the most exciting, exam relevant and concept packed part of this chapter. And let me just tell you that, just imagine you have a haloalkane, right? And you are just removing one, you are having one alkane and you are removing one hydrogen when replacing it with the halogen, and then boom, these powerful molecules, haloalkanes, are produced and they can show enormous types of reaction, substitution reaction, elimination reaction, etc, etc. Now these molecules, okay, they in this part we will be studying so many new concepts like SN1 reaction, SN2 reaction, what is a Grignard reagent, what is Woods reaction. So many reactions we are going to study. And one very important thing is, from this particular part, every year in KCET examination as well as in PU2 board examinations, you will be getting questions undoubtedly. Okay, so most important class is going to be happen today. So let's start this with full confidence, full clarity. Sit with your notebook and a pen, and if you are ready for the class, put a thumbs up in the comment section. But before going to the class, we have a tradition, right, that we should be following. So like the last two classes, in the last class also, you people have really made me very happy with your comments, with your correct answers. I can see so many students participating. Even when the class was going on live chat section also, so many answers were there. So I always promise that I will be acknowledging you people, recognizing you people, and wishing you all the best. So here's the list of the winners of the last class, where we have these many comments. Okay, so I'll be reading each of your names. So I have here first one, Nitya S. Okay, she or he has given a comment. I scored 20 out of 20. So that is really good, dear, and I'm very congratulations and kudos to you. Next we have again Nitya. Ma'am, your teaching is very interesting. Thank you so much for your efforts. So dear, I am very delighted that whatever efforts I'm putting, that is really reaching out to you. You people are getting interested in the class. That is something which is really that makes me happy. Second, we have here Moment Maker. Ma'am, your teaching is amazing. Will you teach PUC syllabus also? So yes, dear Moment Maker, I'll be taking the entire, all the chapters will be covered. So don't worry, PUC syllabus will also be covered. Okay. Next, we have here Sagar Anmol Chopra. Very interesting class. So Sagar has been replying to so many answers also. He has many comments. I have some other comments of Sagar as well. Yes, I scored 19 out of 20. So kudos, Sagar. Just one question, doesn't matter. This is a learning process. And yes, here we will do mistakes and we will learn from our mistakes, right? So congratulations to you also. Next we have Manvita Reddy. Homework answer she has given 1D, 2B and 3C. So congratulations Manvita, kudos to you also, and you keep learning like this. Okay, so I have remembered you. You were in our I think in the Menti quiz session also you were there. I still remember your name. And we have Austin here. He is also a very consistent learner. Last year also, last video also I have seen his comments. In 24th minute he has given the answer. Then we have here Ashwini Ashwini, your 6496. Okay, so here also homework questions 1D, 2C and 3C options. He has also answered the questions. So kudos to you for getting the attempt. Okay, for making the attempt. That is something which is really important. Next we have here Austin has given some more comments. 5 out of 5 at 25 minutes. Nitya S has given 5 out of 5. Then we have Loki Raj. So this is some student which is a new commenter. Last video it was not there. So Loki Raj has also given the homeworks question answer 1D, 2B and 3C. Kudos to you, dear. Then we have R Revati RCL. She has also given commented. So and I think I have Prajwal. Okay, Prajwal I have missed. He is a consistent from the first video itself. Markovnikov rule. He has written what I have told you to remember how to the Markovnikov rule, the shortcut. He has written that also. Okay. Yes, so I think I have read all of your comments. So I thank all the students who have attempted the homework section, attempted the quiz, followed my instructions, put down in the comment section. Thank you so much. Okay, this little effort, you don't know how much impact it put in my life, how much impact, how much motivation I get from seeing your comments. This really, like, I cannot just describe in words what does these comments mean to me. So thank you once again, and now let's move to the next class. So for those students who are watching this video, if you also want your names to be here, please be active in today's class. Whatever I'm saying, anything you have doubt, you just need to put comments here so that it will be clear, it will be reflected in the next video. Okay. And one interesting thing I'll tell you about today's class. I have some interesting stories for you people. Okay, so okay, let's start here. Okay, so first of all, in the previous classes we have what all things we have completed, that is there. So I have already said hello to haloalkanes, haloarenes, their preparation and their physical properties. So what we will be doing today? So in today's class, you can see here that we have this chemistry. Okay, we have RX and ARX, means haloalkanes and haloarenes. Now these are the different things which are, so today we are not preparing. Okay, it is all, last class we prepared, now we have stored it, it is already prepared. Now we are having different chemicals and we will mix them to here and we will see what new products are formed today. Okay, so we are putting these chemicals here. Now we will be mixing it and we will be seeing what new products we will be getting. Okay, so that is all about today's class, chemical reactions of haloalkanes. Okay, fine. So today's class reactions of haloalkanes. So here a small change in the parts I have made. Earlier I thought we will be completing it in 3 parts, but I found that today's class is going to be very important. It should be more focused on understanding the concept than completing the syllabus. So I have extended one more part. So in the next part we will see reactions of haloarenes and polyhalogen compounds. Today's class we will see only the reactions of haloalkanes, and around if I remember, around 25 questions are there in today's quiz. Okay, so fine, let's move. So first of all, haloalkanes is saying to all of us that please remember that I react in 3 different ways. Okay, means haloalkanes can show 3 different reactions. Now ma'am, what are these 3 reactions? So let me show you. Okay, so we have nucleophilic reactions, elimination reaction and reactions with metals. Okay, what are they? Nucleophilic reactions, elimination reactions and reactions with metal. Let me give you a mnemonic to remember here. Just a minute. Yes, nucleophilic, electrophilic, reactions with metals. Okay, NEM. All of you, now please put down a comment section NEM. And why am I telling you to comment is so that you don't get distracted. You are focused in the class only. Okay, what the concepts that I am discussing. So nucleophilic, elimination and reaction with metals, NEM. Okay, so we will be covering all these 3 reactions in today's class. Now let me tell you, this nucleophilic reactions is something which is very important, and majority of the questions will be asked from here. Okay, fine. So bacha log, let's move forward. Now here many of you might be thinking, Ma'am, nucleophilic reactions, right? Nucleophile, this word I have heard sometime the other, right? Sometimes I have heard this word, but I can't recollect, ma'am, what was it? Anybody who remembers what is a nucleophile, you can put down in the comment section. So these students are definitely those who were very sincere in their class 11th. So I'll be telling you, if you don't remember also, please don't have to worry. So, can you see this photo and imagine something? Can you, what we say, picture reading? Can you just see something and recollect what can be a nucleophile by seeing this picture? By seeing this picture, you should be able to now recollect. Okay. So, what I am seeing, a nucleophile, and what it is surrounded with? It is surrounded with electrons, right? So, what are nucleophiles? Nucleophiles are the electron-rich species, means these are those species who are very rich with electrons. Okay, they have so many electrons with themselves. You can see here, so many electrons are surrounded with a nucleophile. Okay, so nucleophile are those species which are having excess of electrons with themselves. Okay. Now, therefore, they attack at that part of the substrate molecule which is electron deficient. Now, as you know, plus or a positive sign attracts a negative sign, right? There's an attraction between the opposite charges. Similarly, since this nucleophile is highly electron rich in nature, it will be attracted or it will be reacting with electron deficient species. Okay, electron deficient means those species where we don't have or where we have less electrons. So now we understood that nucleophiles are the species which have a lot of electrons with themselves, and they react with those species which are poor in electrons. Okay, opposite things will react with each other. Now coming to the next thing, the reactions in which a nucleophile replaces already existing nucleophile in a molecule is called as nucleophilic substitution reaction. So now I'll be telling you, we have seen in the last class the nature of CX bond, right? I have told you that Rx is there because X is more electronegative, it is slightly negative in charge, and this one is slightly positive in charge. So this is what? This is electron rich and this is electron deficient, right? And we have a nucleophile which is very rich in electrons. So what will happen? A reaction in which a nucleophile replaces the already existing nucleophile. Since this is also electron rich, this is also I can say already existing nucleophile. This is electron deficient. So what will happen? This nucleophile will attack on this R and this X will go out. Okay, so these type of reactions where the X group is replaced by a nucleophile is called as a nucleophilic substitution reactions or nucleophilic reactions. Okay, so you can see here we have Rx, right? Then we have this nucleophile. What is the speciality of this nucleophile? This is electron rich in nature. This is also electron rich, but this is more rich than this one. This is richer than this one. Now what will happen? This Nu replaces the X group, right? So that is why, and we have this X minus. Now since this X is leaving the compound, we also have a special name for this X group, and this X name is called as leaving group. Okay, so what is there? What is nucleophilic substitution reaction? In Rx, in haloalkanes, the X group is replaced by a nucleophile. Okay, so those type of reactions are called as nucleophilic substitution reaction. Bacha log, this is clear to all of you. Okay, what is nucleophilic reactions? Now we will move to the next part. So here can you see something? What is this indicating? Can you see something? There are two faces, right? There are two faces. You know, some people are there who are having two faces. Two faces means they are something, they are having one nature and they have another nature. They will be speaking very good with you people in front of you. In your back, they will be talking bad about you, right? So there are two faces for these type of people. Similarly, there are certain nucleophiles who have two faces. Okay, means they can react from two sides. Okay, for example, or just let me first give you an example. These type of nucleophiles are called as ambidentate nucleophiles. Now what is ambidentate nucleophile? Groups like cyanides or nitrites possess two nucleophilic centers and are called as ambidentate nucleophile. So for example, if you see CN, okay, This is Rx. Okay. Now Cn can react from this N group also. Okay. Sorry. The Cn, just a minute. Yeah. So what happens here? This N can react on this R, and we also have like this where this C can react. Okay. So you see two phase in the same nucleophile. We have C can also react, N can also react. It has two phases, I can say, like this. Okay. Similarly, you have one more example, NO2. Okay. I'll just write like this. Okay. If I have Rx, sometimes this O can react, and if I have Rx, sometimes this N will also react. Okay. So from both the sides, but one at a time. Okay. It is not that both are attacking at the same side. O is also reacting, N is also reacting. It is not like that. It is at sometimes you have to, it depends on the reagent that you are using. If you give certain type of reagent, then O will react. If you give certain type of reagent, then N will react. Here if you give certain type of reagent, then N will react. Here if you give some other type of reagent, C will react. Okay. So these type of nucleophiles are called as ambidentate nucleophiles. Okay. I hope this is clear to all of you. Moving to the next one. Here what nucleophile is seeing, let's see, meet my family. So there are nucleophiles we understood, right? But there are so many types of nucleophiles, and we need to meet this nucleophiles family also. Okay. So let's see the first one. So here I told you which nucleophile will be generated depends on what reagent you have taken. So for example, if you have taken NaOH reagent, then what will be the nucleophile here? OH minus. Okay, NaOH will give you OH minus. Now in the alcohol, suppose you have this group, I'll just write one example. Suppose you have Rx. Okay, so when you give NaOH, what will happen? This X will be replaced with OH, and you will get ROH. And what is this compound called as? Alcohol. Similarly, if you take NH2O, okay, in that case also what will happen? H2O is the nucleophile, and it reacts here, and we get ROH. This table you have to remember. Now if you take NaOR, what is the nucleophile here? OR. So what I will get? R, and this X is replaced with OR, and you will get ROR, which is functional group is this one, ether group. Next you have NaI. So here the nucleophile is I. If you replace it if you react here, Ri we will get, which is your iodoalkane. Next, if you have taken NH3, then the nucleophile here will be NH3, and here this X will be replaced with NH2, and we will get a primary amine. Similarly, if you take R-NH2, here the nucleophile itself is R-NH2, and it will react here, and you will get RNHR-, which is the secondary amine. Similarly, you can see for tertiary amine also. Now, these four are very, very important. Mark this one, very important. If you use KCN, the reagent obtained is Cn minus. So what will be the product? RCN, and you will have a compound called as nitrile. But if you use AgCN, okay, if you use AgCN, you will get, this is the nucleophile, and you will get RNC, okay, and it is isonitrile. So if I have KNO2, you will get NO2 as the nucleophile here, and here you will get RONO. See, very important, if you use KCN, you will get RCN, but if you use KNO2, you will get RONO, which is called as alkyl nitrite. Okay, but if you use AgNO2, you will get RNO2, okay, which is called as your nitroalkane. Okay, difference is clear. This 4 is very, very, very important. KCN will give you RCN, AgCN will give you RNC, okay. KNO2 will give you RONO, and AgNO2 will give you RNO2, okay. Nitroalkane and alkyl nitrite. Next we have RCOOAg. Here the reagent is, nucleophile is RCOO minus, and this one will give you, here the product formed is RH, and we will get a here the product is RCOOR, and we will get ester as the product. Now if you take lithium aluminium hydride, here the nucleophile is H and you will get RH, which is a hydrocarbon. If you take R dash and M plus, means any Grignard reagent or any metal and R dash is there, here the nucleophile is R dash and you will get RR, which is again a alkane. Okay, so from here the most important are these four which you have to remember. Okay, now we will do a short quiz and this is round 1. So there are total round 4s and total 25 questions are there. In the first round we have just 5 questions. Okay, so all of you need to, you know what you have to do, you have to put the answers, and at the end of this first round you have to put your total scores in the comment section. Okay, let's move to the first question here. Ethyl iodide on heating with AgCN gives the major product as. So I told you AgCN is very, very important. You must be. So I have ethyl iodide. I'll take yellow color here. Ethyl iodide. Okay, it is reacting with what? AgCN. Now AgCN, I told you what I will get? C2H5NC. Right, and this is nothing but isocyanide, that is ethyl isocyanide. Okay, if it was KCN, I will get ethyl cyanide. If it was KNO2, then I would have, sorry, if it was AgNO2, then I will get nitroethane. Okay, so that is why answer is option number B. Next, which of the following does not show nucleophilic substitution of C2H5Br? So to show nucleophilic substitution reaction, the bromine should be replaced with a nucleophile, right? Here you can see, yes, this is a nucleophile, it will generate OH minus nucleophile. This is a nucleophile, Cn minus, C2H5O minus, so this will also give us a nucleophile, this one. But only H, do we have studied any such reactions? No, right? So that means this is not a nucleophilic reaction, option number A here. Okay. Next, the major product of hydrolysis of allyl bromide with aqueous NaOH. So you have allyl bromide. What is allyl bromide? Okay, and you are treating it with OH minus. So what will happen? This Br will be replaced with OH group, nucleophilic substitution reaction. So what will be the product here? Yes, that is your option number A. Okay, now moving to the next one. Now next, let's see the next question. C2H5Br plus NaOH gives you C2H5OH plus NaBr. This reaction is, so we have just seen what is this reaction. This is nucleophilic substitution reaction. So that is why it is option number B here. Okay. Now last question of round 1. Which of the following is a nucleophilic substitution reaction among the following? Okay. So we have to find out which is a nucleophilic substitution reaction. Now here can you see any there is no alkyl group here, so there is no halogen group here, so there is no replacement. So this is not a nucleophilic substitution reaction. Here we don't have again haloalkane, so this is also not there. Can I see here something? Here also we don't have haloalkane, so this is also not there. But here if you see, this is Br. When you treat it with NH3, the Br is replaced with NH2, and we have studied that NH3 is a nucleophile. So that is why this is going to be my answer for question number 5. Okay, so now round 1 is over. How much marks ever you have got in round 1, do comment down in the comment section. Now the class is going to be very, very interesting. I have brought some very nice stories for all of you. Okay, one story is there for all of you in today's class. Okay, now we have understood that when Rx is there in presence of a nucleophile, when I have an Rx and if there is a nucleophile, it gets converted to RNU and this X minus is left out, okay, or it is removed from this compound. But to do this, to happen this, there are 2 processes, okay. The first one is called as SN2 mechanism and the second one is called as SN1 mechanism. Now here you can see a small break is there, okay. Later I will tell you what is the reason for this, or later you can comment me why this is in 2 parts, okay. So this is SN2 mechanism, this is SN1 mechanism. Means to change or to replace this X group with a nucleophile, it is not that easy. There are 2 different ways of doing this and 2 different ways are called as SN1 mechanism and SN2 mechanism. SN1 represents nucleophilic substitution 2 and here nucleophilic substitution 1. First we will study about SN2, then we will study about SN1. So now let's start this SN2 mechanism with a very interesting story. Okay, so there were two friends. Okay, what was their name? One was R and one was X. Okay, these were two friends. You can imagine your best friends in your life. Okay, so there is one R and there is X. Okay, you are R and here X is your best friend. Okay, not any X. Okay, don't think about your X, think about your friend. Okay, now coming to this one here, what happens, there one day they were playing and they met a new friend coming to their city. This new friend name was Nu or nucleophile. Okay, so we have R and X, two friends were there, and nucleophile was there, a new friend who has come to the city. So we have nucleophile, this is a new friend who has come to the city. Now what happened is, when they three became friend, okay, now this nucleophile also came closer to them and these three people became friend. Now what did this R did is, R was getting more friendship, or it was becoming more closer to NU, and that is why this X was feeling sad. Okay, what happened when these three became friends, R and NU became more closer friends and X was not that close to now R as it was before. Okay, so after some days happened, okay, after few days what happened, R and NU became friends, very close friends, and X was, what was happened to X? X was removed from their friendship. This three friendship now became 2 + 1. So what we understood in this story, so this type of reaction is called as SN2 reaction mechanism, means the R and X was already there, a new nucleophile comes, three of them become friends, and after some time the X is I can say ignored and X is kicked out and R and NU remain as friends. Okay, so this you have understood. Now let's see when I'll tell you SN1, you will see the difference here. Okay, okay, now let's come to chemistry. Okay, just forget about your X, forget about your friends and come back to chemistry now. So what we have here, so you have this compound which is RX. Okay, now what happens, a new friend came, that is nucleophile. Next, this three of them become friends. That when these three of them become friends, it is called as a transition state. What we call them? Transition state. Okay, now generally carbon can form only 4 bonds, but at this point of time when this transition state is there, carbon forms 5 bonds. You can see 1, 2, 3, 4 and 5. Okay, now when this new bond is formed, when these 5 bonds are formed, the compound becomes unstable. So one bond has to break, and that is the reason why this RX bond is broken, and this new bond is formed here and this bond is broken. Okay, this type of insertion or this type of removal of X and then coming of NU. Okay, so this type of reaction is called as nucleophilic substitution reaction 2. Okay, now why we call it 2, that also we will discuss. Okay, okay, so now what happens here, you will see a real example. Suppose I have this molecule CH3Cl, OH minus is a nucleophile, so this was R and this is X. They were very good friends. Now OH minus came in their life, so as a result what happened, OH also tries to be friend with R, and these three of them became friend here. But after some time what will happen, these two will be friend and this one will be kicked out, and you see a compound like this, right? So this is SN2 mechanism. Now let's understand some more points about SN2 mechanism. So first of all, the reaction type is SN2. What is the kinetics here? So just let us understand, when the reaction is happening, it depends on what factors, that is important. So when this reaction is happening, both Rx is also present and Nu is also present, right? Rx is there, Nu is there, and so that is why the reaction rate will depend on the concentration of both Rx and Nu. Since it depends on both of them, it is a bimolecular reaction and we call it as a second order kinetics. Now when you study the chapter chemical kinetics, this will be more clear to you. Okay, so we have Kinetics follows second order because the rate depends on both the nucleophile and the alkyl halide concentrations. Next, what are the steps involved? It is a single step reaction, means exactly when I show you, this is the step of the reaction. You can see here, this is one step reaction. Nu is present, Rx is present, they both form a bond and then one bond is broken. So this is the reaction step, this is the intermediate and this is the product. So the reaction happens in a single step here. Okay. Next, what is the transition state? The carbon is partially bonded to both the incoming nucleophile and the leaving group. The X is called the leaving group, and that is why carbon has 5 bonds at this time. So it is at a transition state, or this is unstable state. Next, carbon structure. That what is the structure here? You see this structure. If you see this one, in this transition state, the carbon 3 bonds, okay, are in one plane. All the 3 bonds of carbon are in one plane. Okay, that is because carbon has a tetrahedral structure and 2 bonds are in one plane and 2 bonds will be in the other plane. But when this transition state is formed, all the 3 bonds are in one plane and the 4th bond and the 5th bond are in different plane. Okay. Okay, all the 3 CH bonds lie in the same plane during the transition state. Next, what is inversion of configuration? That we will be understanding in detail after some time. So the carbon shape flips like an umbrella in the strong wind. This is called as Walden inversion. Now I will explain this term after some time. Okay, we will come to the stereochemical aspects after some time, so you have to wait for that. Now, effect of bulky groups. Now what happens? Bulky substituents near the carbon make it hard for the nucleophile to attack. So reaction slows down. Now if you see the reaction mechanism, yes, what you see here, this nucleophile is going to attack on this carbon, right? Now just imagine that here some big groups are present. Okay, then can this nucleophile come and attack this carbon, or can this nucleophile make friendship with this carbon? No. So what is the condition we require? That the groups, the other 3 groups which is present in the carbon, these 3 groups should be smaller in size. Okay, then this nucleophile has some space to attack here. If these molecules are very big, okay, if these molecules are very big like this, okay, then this nucleophile cannot enter from anywhere. Okay, so that is why what we can say is the smaller the molecule, better is the SN2 mechanism. Okay, so what is the order here? The order is 1 degree, then 2 degree and then 3 degree. Okay, 1 degree will react faster, then 2 degree and then 3 degree. Now moving to the next one, that is SN1 mechanism. So again we will see the same story but in a different way. Okay, so what happened here? R and X were very good friends. Okay, they were very good friends. They were living happily, sharing everything with each other. They were very close friends, like you and your best friend. Now after that, what happened? One day nucleophile came to their their city and a new girl was there. Now seeing this nucleophile was very rich, right? So if you remember, let me just tell you the story like this, that this nucleophile was very rich girl. Okay, so what happened, just when this R came to know that this nucleophile is there and she is very rich, what happened? R immediately wanted to make friendship with nucleophile. In the previous case, what happened? There was some time, the 3 of them were friends for some time, and after that this X was kicked out. But here what will happen, when this R saw nucleophile, immediately it was tempted, because whatever chocolates, pens, pencils this nucleophile will bring, it will definitely give to R if R is his or her best friend. So thinking that, what R did, R immediately broken friendship with X. Okay, so there was no more friendship between R and X. Okay, immediately the friendship broke there. Okay, and after that R and Nu became friends and they were present. Okay, so what you understand here, in the first case, R, Nu and X, or I can say Nu, R and X were friends together for some time. Okay, means there was a transition state where X and Nu both are attached to R. But here that situation does not arrive. Immediately when nucleophile arrives, R and X friendship breaks and R and Nu friendship is formed. Okay, so that is what is SN1 reaction. Now if we see in this reaction, it will be more clear. So in the first step, what happens? R and X bond is broken immediately. Okay, R and X bond is broken. Now when R and X is broken, we get a carbocation here. Okay, this type of species is called as carbocation. Now in the second step, what happens? Nucleophile has come here. Now you see in the first step there is no nucleophile. Okay, so just let me just tell you the story like this. Okay, here I'll go back and little bit modify the story. So R and X were friends. What happened after that is R heard news. R heard the news that nucleophile, a friend, a girl, a very rich girl is coming to their city. Okay, then immediately what happened? R and X friendship broke. Okay, after this what happened? R and X friendship broke. Then nucleophile, the rich girl, came to the city and these two became friend and the new friendship became. Okay, so what happens when I tell you here the reaction, it will be more clear. So now here this compound heard the news that a very rich nucleophile has come in this surrounding. So what happened? Immediately their friendship broke, and once the friendship broke here, in the step 2 what happens? This new nucleophile attacked here and then there is a new bond formed. So here you see the reaction is taking place in the 2 steps. Okay, earlier the reaction was taking place in 1 step. Here the reaction has taken place in 2 steps. First there is a bond breakage of R and X, and second step is the formation of new bond R and NU. But if you compare SN2, there was no bond breaking of Rx. NU and R were together, NU and X were together with R at the same time, and after some time R was released. Okay, after some time the X was kicked off. Okay, so the story is just to make you understand the concepts, but you have to understand in detail in the reactions. Okay, now let's understand some facts about this reaction. So reaction type, it is SN1. This is called a first order kinetics. Why? Because here the rate will depend only on the concentration of Rx. So when the reaction has started, okay, at that time there was no nucleophile present. Okay, there was only R and X, means that only alkyl halide was present. After the alkyl halide Rx bond is broken, then the nucleophile comes to the play, right? If you see this reaction mechanism, in the first step, this is the slow step. Okay, always remember that the rate is determined by the slowest step. Okay, so this is the slow step. Here the reaction has happened, and after in the second step OH minus has come. So in this rate determining step, or in the slowest step, there is nowhere presence of nucleophile. So the nucleophile is not determining anything regarding the rate of the reaction. So that is why the rate is a first order reaction and it is written SN1 reaction. Okay, next, steps involved. So there are 2 steps involved. The slow breaking of the carbon bond C-Br bond to form a carbocation, that is the first step, and in the second step the nucleophile attacks the carbocation. Okay, next we'll talk about the solvent. So generally what happens, this type of reactions take place in polar protic solvents like water, alcohol or acetic acid. Polar protic solvent means, polar means, you know, there should be charge difference. Protic solvent means those solvents which can give you H+. Okay, for example, water can give you H+, alcohols can give you H+, acids can give you H+. So these type of polar protic solvent is required for the SN1 reaction. Next, carbon stability. So here what happens, since the intermediate is formed, carbocation intermediate is formed, 2-step reaction. In the first step the carbocation intermediate is formed, so more stable the carbocation, faster will be the reaction. And we know that 3 degree carbocation is more stable than 2 degree than 1 degree. Now if you don't remember this one, this is from class 11th, so if you know, comment down in the comment section why 3 degree is more stable than 2 degree than 1 degree. Okay, I'll be answering this in the next class. Next we have some special cases also. So if allylic or benzylic halides are there, their carbocations are much more stabilized due to resonance. So that is why they will undergo also faster SN1 reaction. Now let me explain what is this part. So if I have a allylic, okay, allylic, that means what, this X will go out, so here a carbocation will form, and now this carbocation is stabilized due to resonance. So allylic carbocations are very stable and undergo SN1 reactions easily. Now if I have the next one here, benzene ring, here you have Okay, here once X goes, here also positive charge will flow and positive charge will flow, and this is also resonance stabilized. Okay, now what is the order here? Order for this one is Ri, Rbr, Rcl and Rf. This order is 3 degree, 2 degree, 1 degree, and if you have same R and the halogens are different, then iodine, then bromine, then chlorine, then fluorine. Why? Because first step is what? The bond should break, and Ri bond is weaker. We have seen in the physical properties. So Ri will be easily breaking, and that is why this will react faster. Okay, so now we'll do certain quizzes here. Okay, so we have how many questions? We have almost 8 questions here. Let's do it quickly. So the first one here is, okay, which of the following is the example of SN2 reaction? Okay, so in SN2 reaction, what should be the order? 1 degree, 2 degree and 3 degree, right? So let's see, we have CH3Br OH-. So this is 1 degree, this is 2 degree, right? This is not an alcohol, this is 3 degree. This is not a haloalkane. Okay, so this is 3 degree. So 1 degree will react faster. So option number A. Next, we have predict the order of the reactivity of the following compounds in SN1 reaction. So what you have to remember, 3 degree, 2 degree, 1 degree, right? For SN1. For SN2, it is reversed. This is which degree? This carbon which contains the chlorine is attached to 2 other carbons. So this is 2nd degree. This carbon which contains the chlorine is attached to 3 other carbons. So this is tertiary. This is also tertiary, right? 1, 2, 3, and this is also tertiary. So basically tertiary will react faster than secondary. Now when you have the same R group, what you have to check? The halogen group, and we have studied that iodine will react faster, then bromine, then chlorine, then this one. So what will be the order? 4, 3, 2, 1. Okay, so option number A. Okay. Let's see the next question here. For I minus, Cl minus and Br minus, the increasing order of nucleophilicity would be. So we have seen I minus will react faster, then Br minus, then Cl minus. So it is option number A. Next, the correct arrangement of the following alkyl bromides in order of their decreasing reactivity in SN2 reaction. So what is the order of SN2? 1 degree, 2 degree and then 3 degree. So I cannot find here 1 degree is first, right? So this I can eliminate, and here it is 3 degree, I can eliminate. After 1 degree, I have here also 1 degree, here it is 3 degree. So this one will also be not there. So this will be the correct answer. 1 degree, 1 degree, then here 2 degree, here also. Okay, all of them are actually, okay, this is 3 degree, okay. This is 1 degree, this is 1 degree, this is 1 degree. But you should remember the steric hindrance should be less, right? So here we have less steric hindrance, then here we have more steric hindrance, then here we have more steric hindrance because of this group is present here, right? Okay, next we'll go to 10th question, the decreasing order of SN2 reaction for the given compound. Decreasing order of SN2. Again we have to see. So first of all we should have primary one. Okay. So if I see this is primary, this is also primary, this is also primary, but this is bulky, right? So fourth one should be at the last. So where I have fourth one at the last, I can eliminate these two options. Okay. Next, next compound, this one should be at the highest because you see this is a less bulky group is present. So one should be highest. So I have only one option like that. 1, 2, 3 and 4. Okay. So that is why option number A is correct here. Next, which of the following shows SN1 reaction most readily? So you should note that tertiary group will show most readily. Here I have a tertiary group, so that will react faster. So option number B here. Next, which of the following compound undergoes SN1 reaction readily? Okay, so for SN1 reaction, these all are having benzylic carbocation, right? These all are benzylic carbocation. Now see, a nucleophile should attack on these rings, right? So that means what? This ring should be more and more electron deficient. The where electron deficiency is more, there the reaction will be faster. Now if you see here, in this case, this is electron donating, which reduces the electron deficiency of the benzene ring. This is also electron withdrawing, right? It also, this is electron withdrawing. So it increases the electron deficiency of this ring. Next here, this is also electron donating. it reduces the electron deficiency. Here there is no effect. So since NO2 is present, which is electron withdrawing in nature, it makes the ring more and more electron deficient. So nucleophile will react in that case where the electron deficiency is more. So here, because it is electron withdrawing group, electron deficiency is more. So that is why option number C. This is electron donating group. Okay, this is electron donating group, and this is also electron donating group. So these two, what they do, they reduce the electron deficiency of the ring, and that is why the nucleophile will not react. Next, we have the order of reactivity of the following compounds in SN1 reaction. Okay, so you have C6H5CH2Br. So you have like this in SN1 reaction. The first compound given to you is this one. The second compound is C6H5CH6H5Br. So you have like this. Here you have one C6H5, and here you have, okay. Next you have C6H5CH3Br. Okay. Next we have C6H5CH3C6H5Br. Okay, you have one more CH3 group. So now if you see that in this case, okay, here you can see that this carbocation which is formed, that will be more stabilized because we have two phenyl groups here, right? So this one will be highly reactive. So where I have that option in the last, C6H5 CCH3 C6H5Br. So that will be the last one. So that has to be the correct answer. So option number B here. Okay. Yes, and the least one will be C6H5CH2Br, then we have this one, then we have this one, and lastly we have this one. Okay, fine. Now we will go to the stereochemical aspects of the nucleophilic reactions. This is very, very important, and before understanding the stereochemical aspects, we have to understand certain terms. What are these terms? Optical activity, molecular symmetry, chirality, enantiomers, retention, inversion, retention, and racemization. So please don't worry, I will be explaining all these concepts in very, very easy terms so that you will understand it. Okay, so first let's talk about, well, okay, first let's check this one video that I have for you people. Okay, just a minute. Okay, so now before understanding these concepts, let's watch this video and understand what is plane polarized light. Okay, so first of all, you see this is a light, okay, and light has a different types of, I can say, magnetic field, electric field, right? It has so many different fields of light, and this is one instrument which can filter out the fields of this light. So lights have field in all these directions. You can see you have green light, blue and red waves. Means these are three-dimensional, three types of fields are present. Now what happens? This is unpolarized light. Now when this unpolarized light passes through this particular instrument, what happens? You find only one type of field is remaining. So this light, okay, where you can see this was having all types of field, okay, all types of field was present, and after that you see after passing through this instrument you find only one type of field is present. Now this light which has only one type of field is called as plane polarized light. Okay, now why we are talking about this plane polarized light, we will be discussing in the next slide. Okay, see. Now what happens? We have got this light is there, okay, it is having fields in all the direction. Then when you pass it through this polarizer, you have only one field, okay, the field is present only in one direction. Now you pass it through one organic sample. If this organic sample is able to rotate this plane polarized light, then we call that molecule as optically active. Okay, what is an optically active molecule? A molecule which can rotate the plane polarized light. Okay, so now that is what we will be understanding here. So if a compound rotates the plane polarized light to the right direction, then we call it dextrorotatory, or it is represented with positive sign or a small d. Okay, and if the organic compound, the organic sample here rotates the light in the anti-clockwise direction or in the left direction, we call it levorotatory or L form, or the negative sign is represented here. Okay, this is clear. So now, plus and minus isomers of a compound are called as optical isomers, and this phenomenon is called as optical isomerism. Okay. Now we'll move to the next term, that is what is an asymmetric carbon. Now see, so first of all, if any compound or any carbon is there, which is carbon has 4 bonds. So if one carbon has 4 different groups attached to it, means all the 4 groups that is attached to the carbon are different in nature. Okay, there are different groups are present, then that type of carbon is called as asymmetric carbon. Okay, so what we understood, what is an asymmetric carbon? If all the substituents attached to that carbon are different, then we call it an asymmetric carbon or stereocenter. Now, if a carbon is asymmetric, then what will the consequence? The mirror image of that molecule is not superimposed. Okay, first let us explain. So first what I am saying, that if all the substituents attached to the carbon are different, then it is called as asymmetric carbon. This is clear? This would be the definition of asymmetric carbon. Now, if this happens, if a carbon is there which is having all the 4 groups different, in that case what happens? The mirror image of the molecule is not superimposed. Now, what does that mean? I'll give you an example. Suppose you have a letter K. Okay, if you have its mirror image and you try to superimpose one on this one, you see they are not superimposing on each other. So if I have a carbon molecule which has 4 different groups attached, then they will never superimpose on each other. And suppose here you take an example of letter W. Okay, its mirror image and this one is there. If you keep this on this one, exactly they will superimpose. So this phenomenon of not having superimposing mirror images is very important, and we have a special name for that. Okay, so whenever we have a carbon which is having 4 different groups, that is called as asymmetric carbon or a stereocenter, and that particular molecule is called as asymmetric molecule. Now we will talk about this mirror image. Now see, the objects which are non-superimposable on their mirror images are said to be chiral. Okay, so if a carbon is having 4 different groups, then it is called asymmetric carbon. But if this condition is fulfilled, then it will never superimpose its mirror image, and that phenomenon is called as chirality, or chiral, or that carbon is called as chiral, and this property is known as chirality. Now here what is interesting, the asymmetric nature of the molecule along with the chirality of the mirror images is responsible for the optical activity in such organic compounds. So now what we said, see in the previous slide, if I go, I said that if this molecule is able to rotate the plane polarized light, whether in left direction or in the right direction, we will call it as optically active. But do we have to always go to the lab and check that, put the molecule in the sample, do this experiment, and then only we can decide whether it is optically active or not? It is not like that. We have a shortcut for that. What is the shortcut? This is here. So if you have a molecule which is asymmetric, what do you mean by asymmetric? What do you mean by asymmetric here? Means if a molecule is there which has a carbon which is 4 different groups, then it will be chiral. Chiral means its mirror image will not be superimposable, and these type of molecules will be rotating the plane polarized light, or they will be optically active. Okay, I hope you are clear with 3 terms. Optical activity, what is that? It means those molecules which can rotate the plane polarized light. That is called as optical activity or optically active molecules. Now how will you know whether a molecule will rotate the plane polarized light or not? For that, the carbon should have 4 different groups. This property is called as asymmetric carbon, and its mirror image should be non-superimposable, and this property is called as chirality. Okay, so chirality plus asymmetric center results in the optical activity of a compound. I hope this is clear, very, very clear, 3 terms. Okay, now we will see the next thing, that is enantiomers. So now I told you the stereoisomers related to each other, such as their non-superimposable mirror images of each other, are called as enantiomers. So for example, if you see this letter K, right? So this letter was there and its mirror image were non-superimposable. So now this pair are called as enantiomers. If you see a molecule here, Okay, this molecule was there. This is carbon with 4 different groups. Its mirror image is this one. These two are non-superimposable. So if they are non-superimposable, this pair will be called as enantiomers. Okay, so enantiomers is always with respect to the pairs. Okay, so what is enantiomers? You can see here I have taken a molecule D-alanine. Okay, now when I draw its mirror image, this mirror image is not superimposable on this one, and it also has 4 different groups. So these compounds are optically active. That is clear. Now this pair together will be called as enantiomers. Okay, the stereoisomers related to each other as non-superimposable mirror images are called as enantiomers. Clear? Now let's move to the next thing. So what is some properties about enantiomers? So enantiomers are, they are identical physical properties. Okay, they have all the properties like their boiling point, melting point, everything is same, but they have one physical property which is different. That is the only differ with respect to the rotation of plane polarized light. So the two compounds which are non-superimposable mirror images of each other, which are enantiomers, they have one property different. That is, one molecule will rotate the plane polarized light in clockwise direction, then the other one will rotate it in anti-clockwise direction. Okay, I hope this is clear. Fine. Next, so now we have one more thing. If you have a mixture where both these compounds are present, okay, 50-50% both these compounds will be present. Okay, like for example, if we go to our polarimeter, just a minute. Yeah, so now suppose in this particular compound you have both the enantiomers. Okay, one is plus, one is minus. Okay, now both are rotating in equal direction, and these are present equal and opposite direction, and they are present in equal amount. So what will be the net result? See, suppose the light is passing. Okay, the plus one rotated to some angle, then again the minus one will rotate it back, again plus one will rotate here, minus one will rotate. So the light will remain as it is while passing through it will not be like this tilted, because both the groups are present in equal amount. So in that case, or these type of mixtures are called as racemic mixture. Okay, so we have a mixture containing two enantiomers in equal proportions will have zero optical rotation, as the rotation due to one isomer will be cancelled by the rotation of the other. Such a mixture is called as racemic mixture, or this phenomenon is called as racemization. Okay, I hope this is clear. So I just want to take 1 minute to recollect everything. First of all, we studied about optical activity. Now what is this? Is optical activity property to rotate plane polarized light. Now when this property, which compounds will have this property? You should have two conditions for that. One is asymmetric carbon, and the other one is here chirality. Okay, so if these two phenomenon are satisfied, then that molecule will be optically active. Okay, now there chirality means what? The molecule and its mirror images will be non-superimposable, and asymmetric means what? The carbon should have 4 different groups. Now when this condition is fulfilled, this condition is automatically fulfilled. Okay, generally it is fulfilled automatically. Now when this two mirror images are there, this pair is called as enantiomers. Okay, I hope you are clear with all these terms, right? Fine, let's go back then. So next we will understand what is retention. Now see, retention means if this is, you can see now this, I'll explain the concept here. So you have this carbon, so it has 4 different groups, right? So that means this is an asymmetric carbon, or it is a stereo center. Now if after the reaction also, the stereo center or the configuration of all the groups around this carbon remains same, then we call it as retention. So if you see here, so generally when we can observe retention of a configuration is the preservation of the spatial arrangements of the bond. Means how the bond were present before the reaction, it should be present exactly the same after the reaction. Then we call it retention. Now in general, when can we observe retention? in general, if during a reaction no bond to the stereo center is broken, means you see any bond which is attached to this stereo center is not broken, in that case we have retention. So for example, if you see this reaction, we have OH and then HCl, so this bond is breaking, but the bonds which are present to this particular stereo center are not involved, right? So this one will break and you will get Cl. So you can see that the retention is maintained, the retention of the configuration is same here. Okay, whatever was the configuration before, the same is the configuration after the reaction. Same means the bond arrangements, means it has two bonds towards the up and two bonds in the plane. Here also it has two bonds towards the up and one bonds to, sorry, you have, I have just, yeah, so it has two bonds to away from the plane, one bond behind the plane and one bond in the plane. After the reaction also we can see the same configuration, so that is why the retention is happened here. But here you should be very careful that retention doesn't mean that the direction in which it will rotate the plane polarized light, that is also constant, that may change. Okay, here it was minus, here it became plus, means now earlier the molecule was rotating in clockwise, anti-clockwise, now it is rotating in clockwise, but still the configuration remains the same here. Okay, that is retention. Now let's talk about inversion, retention and racemization with respect to our SN1 and SN2 reactions. Okay, so students, I can understand you might have feeling this little bit difficult, but don't worry, just keep revising, look this video once again, it will be more clear, and it will be more clear when we do some questions on this. Okay, so first you see this reaction is there, okay, and you have added a reagent Y to all these cases. Okay, now when you add Y, what will happen? In the first case, what has happened? See, the H has come front and Y has attacked from the back side. If you see, the Y has attacked from the back side. In this, what you see in the first one, you have seen where X was there, in the same position Y has come. So can you see that this is the stereo center? Okay, this is the stereo center, and the bond configuration here is exactly same how it was before the reaction and after the reaction. So this is a case of retention. Okay, now if you see here, if you see the bond configuration, it has now changed. How the bond was there before, and now the bond is not like that. Earlier what you have observed, earlier we have seen that the X was on this side while this Y has come to this side, and the configuration has changed, it has now different from the previous one. Okay, so that means now this is called as inversion. Okay, when you have A and B both, that is you have A also, retention also, inversion also, we get a racemic mixture here. Clear? So now we'll see what happens in SN1 and SN2 reaction. So if you see, this is SN2 reaction. In SN2 reaction, what is happening? The OH minus attacks from the back side. Okay, it attacks from the back side and the configuration changes here, and this is an example of inversion. So you should remember that in SN2 we have inversion. Okay, now if I take the next one, here there is an SN1 two-step mechanism. First there is a formation of carbocation, and once this carbocation is formed, what happens? The molecule becomes planar. Okay, the molecule is completely planar here. So now this OH minus, you can see this is a planar molecule now. The OH minus can attack from both the sides. Okay, so if it attacks from both the sides, you will get both retention product and inversion product, and you will get finally a racemic mixture here. Okay, here you will get a racemic mixture. So what I wanted to say here, something important, is why this OH minus always attacks from the back side. Can we have a reason for that? Yes, see, OH minus cannot come from the front side because bromine is present here, which is a very bulky molecule. So here we have H and smaller molecules, so OH tries always to attack from the back side. Moreover, this is a nucleophile, this is also nucleophile, they will repel each other, so it cannot come directly, it attacks from back side. Okay, so when it attacks from back side, we get inverted product. Okay, and in case of SN1, you get a retention product. Sorry, in case of SN1, we get racemic product. Okay, Fine. Now let's do some quizzes on this particular concept. The reaction that is described here. You can see one step reaction, OH minus is attacking here. Which type of reaction? This is SN2 reaction. Next one, we have which of the following is the chiral molecule. So what is the definition of chiral molecule? It should have 4 different groups, and when it has 4 different groups, it will have non-superimposable mirror image. So if I see option number A, I have CH3Cl. 3 groups are same, so this is not there. CH2Cl2, here also I have group same. CHBr3, here also it is not there. If you see CHClBri, all the 4 groups are different. So yes, this is a chiral molecule. Next, 2 possible stereo structures of CH3, CHOH, COH which are optically active are called as. When you have 2 structures, the pair is called as what? Enantiomers, option number B. Next, I have how many chiral carbon atoms are present in 2,3,4 trichloropentane. So if I draw trichloro, 1, 2, 3, 4, 2, 3 and 4. So now what you have to check? You have to check that which carbon is having all the 4 groups different, right? So now if I see this carbon, this is having all the 3 same hydrogen, so it is not there. This is having 4 different groups, so this is chiral definitely. This is also having 4 different groups, so this is also chiral. This carbon, if you see, this side it is chlorine, this side it is hydrogen, but this side and this side are exactly the same group. You have 1C, 1C, 1Cl, Cl, H, H, then CH3, CH3. So how many chiral centers we have? We have 2 chiral centers, that is option number C. Next, we have 3-methyl-pent-2-ene on reaction with HBr in the peroxide forms an addition product. The number of possible stereoisomers for this product is. So, if you have 3-methyl-pent-2-ene, okay, and then it is reacting with HBr in presence of peroxide. So, when it reacts with peroxide, what I will get? You will get a product like this, okay. Now, this is, you can see here, this is a, just a minute, yeah. So now you can see this is it chiral? No, because we have 2H group here. Is this chiral? No. We have this particular carbon, here you can see a different group, here we can see a different group, here we can see a different group. So this is a chiral molecule. Now this particular compound will have its mirror image which is non-superimposable, right? So that means this compound and its mirror image both will be optically active. So we will have 2 stereoisomers here, okay. Fine. Next, we have to match here. Primary alkyl halides prefer SN2 reactions. Secondary alkyl halide, we have to check. Tertiary alkyl halide prefers SN1, secondary SN2 or elimination depending upon the strength or the base. So A has to be 2, I can eliminate these 2, and B has to be 1. So I have A2B1. Yes, so this is my correct option, okay. Next, we have the maximum number of possible optical isomers in 1-bromo-2-methyl cyclobutane. You have 1-bromo and 2-methyl. Okay. Now you see this carbon is optically active, is it? Yes, this carbon is optically active. This carbon is also optically active. So these 2 carbons means for this particular carbon, this one and its mirror image, and if you have this particular carbon, this one and its mirror image. So total I will have 4. Right? This is one optical isomer. Its mirror image will be another optical isomer. This compound will be optically active and its mirror image will also be optically active. So total I will have 4 here. So option number A. Okay. Next, we'll move to the next reaction, that is elimination reaction. So we have 3 types of reaction, right? Nucleophilic, elimination and reaction with metal. So in elimination reaction is very simple. You have a base here, it abstracts a beta hydrogen, and then what happens? A double bond is formed here. Okay. Now there is a rule here that which alkene will be produced. So Saidzef, a scientist, told a rule. What did he say? He said that when you remove a hydrogen and a halogen in case of dehydrohalogenation reaction, the preferred product is that alkene which has greater number of alkyl groups attached to it. So we have already studied a more stable alkene is that which is having more number of groups attached to, in the surrounding of it. Okay. So for example, if I see 2-bromopentane is there. If you remove, you can have a double bond here also. You can have a double. If you remove this H and this Br, this is also double bond. Now what is this beta hydrogen? Beta hydrogen is the hydrogen attached to the carbon next to the carbon containing X group. Okay. So if you have this carbon which is having X group, the next carbon to that hydrogen here is a beta hydrogen. So the base will attack this hydrogen and then you will have this double bond, and this is the alkene formed here. So the Sejzev rule says that always you should form that type of alkene besides which we have more number of alkyl groups. Okay. So now we will see last one, that is reactions with metals. So the first one is the reaction with Grignard reagent. So whenever you take any haloalkane and react with Mg, we get RMgBr. Okay, and this is a Grignard reagent, or this reaction is called as Grignard reagent. Now in Grignard reagent what happens, this RMg bond is a covalent bond, whereas this MgX bond is a ionic bond. Now what happens when this RMgX is present, any water substance is given to this R minus will immediately abstract the H plus from there and you will get RH. Okay, so that is why we should prevent this in like water or moisture should be avoided when you are doing Grignard reagent reactions. Okay, and the last reaction we have is the Woods reaction. In Woods reaction what happens, you have Rx plus Na, and then these two will react to give you RR plus NaX. Okay, so this is Woods reaction where alkyl halides reacts with sodium in dry ether. Okay, so here you have to give dry ether containing double the number of carbon atoms present in the halide. So whatever number of carbons are present, double of that will be formed here. Okay, so this is your Woods reaction. So we have completed all the reactions now, and let's do 5 questions on this particular concept. So here you have been given with OH minus and you have asked with the major product. So Sejzev rule we have to apply. So what all possible products are there? See, this is also alpha hydrogen, this is also alpha hydrogen. Here a double bond can form, here a double bond can form, but the majority will be the double bond that is formed at this place. Why? Because this is where the more number of alkyl groups are attached, or more number of alkyl groups are present towards the double bond. So if you see, this is given, this is the major product, which is wrong, but here you see this is given 81% and this is given 19%. So this will be the major product, option number B here. Next, consider the following reactions. Again, here you have alcoholic KOH. So this is a reagent which does elimination. Okay, dehydrohallucination takes place in presence of alcoholic KOH. So you will get here a propene. Okay, you will get a propene here, and then when you treat it with HBr peroxide, what will happen? You will get CH3, CH2, CH2 and Br. Okay, so the final product that we will get here will be your option number D. Okay. Now moving to the next one, which of the following compounds cannot be used for the formation of Grignard reagent? So for Grignard reagent, we cannot have any of those compounds which is having what? Hydrogen group, right? So which of the following compounds cannot be used for the preparation of Grignard reagent? So we can use this one, we can use this one, we can use this one, but here we cannot use because it is having alcohol group. So that is why option number B. Next, which one of the following alkanes is not formed in Woods reaction? So in Woods reaction, you need the product will at least have 2 carbons. Okay, so methane is having only 1 carbon, so that will not be the product formed here. Next, Grignard reagent are very useful starting compound for a number of organic compounds can be prepared by. So it can prepare reaction of alkyl halides with a solution of magnesium hydroxide, no. Reactions of alkyl halides with dry magnesium powder in the presence of dry ether. Reactions of MgCl2, no. Reactions of alkyl halide with magnesium in presence of alcohol, no. Alcohol is not required. So that is why it is option number B. Okay. So students, that's all, and now we have 3 questions for homework section. You need to do that and comment down your answer section in the comment section, and we will also put down your scores. And thank you for watching, and in the next class we'll be continuing with the reactions of haloarenes. Thank you and all the best.